We are still in chapter 5, and next topic is regression with x as binary or dummy variable. So what is binary or dummy variable? For example, if you have a variable like gender that has two values, male or female, as purchase that someone has bought the good or not, or someone is retired or not, you can designate the values instead of the words. You can designate values 1 and 0. So in that way, we are actually constructing new variable that we call dummy variable. So these are the ones and zeros are actually indicators of dichotomous variables. For example, in our case, with the class size, we will, instead of student-teacher ratio as continuous variable, use dummy variable, where if student-teacher ratio is less than 20, we will put zeros, and if it's equal or larger than 20 students per teacher, we will put number 1. So our model will look like this. We will also have beta 0 and beta 1, but D1 variable will be actually dichotomous variable or dummy variable with zeros and ones. Beta 1 is not the slope anymore. We cannot comment it in the same way as before, but now beta 1 is showing us the average difference between two groups, between groups with less than 20 students per teacher and group with 20 or more students per teacher. So on graph, we will actually have two lines. One will be for beta 0, and it will show the average value for the group with less than 20 students per teacher. And the second, if we have D as 1, we will get another line showing us the average value, average test score for the group with 20 or more students per teacher. So in order to, when we test beta coefficient, beta 1, we are actually testing if it is statistically significant, and also is there statistically significant difference between these two groups according to their test scores. Again, we are expecting that for D1 group, for group with less than 20 students, that expected value will be beta 0, and for the other group, it will be beta 0 plus beta 1. Now, when we test if beta 1 is statistically significantly different from 0, if we accept the null, and our conclusion is that beta 1 is equal to 0, then we can say that there is no statistically significant difference between these two groups. If we reject the null and beta 1 is different from 0, then we have statistically significant difference between these two groups. Okay. If beta 1 is statistically significant, the difference between two groups in population is statistically significant. So test of hypothesis will go according to the same procedure as you already saw. So the null will be that beta 1 is equal to hypothetical value, which is null, 0 in the population, and the alternative hypothesis is claiming the opposite. Again, we will calculate the t statistics, compare it to the 1.96 with the two limits, minus and plus 1.96 as the area of accepting the null hypothesis. We will have standard error, we will have the value of beta 1 hat. We already know that beta 1 0 is actually 0. We can also calculate the confidence interval for beta 1 in the population, in which limits we can expect that average difference between these two groups will be when it comes to their test scores. So this is the example, these are the results. We can skip to Gretel and then calculate it later on. So beta 1 here is 7.4. Standard error of beta 1 is 1.8. So For D1, for the group with less than 20 students per teacher, we can expect the average score of 650. For the other group, if we add up these two coefficients, average test score is 657.4. We will now test beta 1, T statistics, so this is beta 1 hat minus a hypothetical value divided by standard error. Compare it to 1.96, so it is much larger. It is in the area of rejecting the null, so beta 1 is statistically significant. So there is really statistically significant difference in population when it comes to test score between these two groups, with less and more of student-teacher ratio of 20. So, with 95% probability, we are rejecting the null and concluding that there are statistically significant differences between two groups of districts with less and more than 20 student-teacher ratio. Beta 1, 7.4, is showing that average difference in test points between two groups is 7.4 test points. When it comes to confidence interval, it goes according to the same formula. So this is beta 1 hat, this is critical value, this is standard error, and we can expect that the average difference between these two groups in population goes from minus 3.9 points to minus 10.9 test points. So with 95% probability, we can expect the true value of beta 1 in the population will be between 3.9 and 10.9. Let's go to the example. So we have now new variable D1 that we constructed from the student-teacher ratio. Let's see these two variables together. So if it is less than 20, D1 will be 0. If it is more than 20, student-teacher ratio, the value of D1 will be 1. So this is how we created new variable. Now we will make the model. Test scores is dependent variable still, and regressor now will be D1. When we click OK, this is our model, and exactly we are getting as we've seen already in our example. So beta 1 is minus 7.4, standard error is 1.8. This is how we got these results, and this is statistically significant, so it is different from 0 in the population. When it comes to confidence intervals, we go to analysis, confidence intervals for coefficients, and we now see that in population, beta 1 coefficient goes from minus 10.9 points, almost 11, and to minus 3.7 test score points. This is the end of the example and presentation.